Hi everyone, my name is Yifan. It is my pleasure to give a presentation with my partner Qinzi on the exciting work we did with Professor Louis Tseng at Boston College. Our research is about exact consensus under global asymmetric Byzantine links. To give a brief summary, all the nodes in our system are fault-free and each pair of nodes can communicate directly with each other. In the GAB link model, up to F directed links may become Byzantine and have arbitrary behavior. Our model is different from prior ones mainly because we have asymmetric links and we adopt the global constraint. To illustrate the asymmetric link, assume we have two nodes A and B. It is possible that the link from node A to B is faulty, but the link from node B to A is fault-free. Moreover, unlike some priori models with a local constraint, which enforce a local upper bound on the number of failure links, the global constraint allows any link to be corrupted in the GAB model. In our GAB model, we study consensus problems in both synchronous and asynchronous systems. We show that 2F plus 1 nodes are necessary and sufficient for solving synchronous consensus, while 2F plus 2 nodes is the tight condition on resilience for solving asynchronous consensus. For synchronous consensus with mobile faults, 2F plus 3 is the tight condition on resilience. Now let's take a closer look at the system model. Our system is composed of n fault-free nodes connected to each other to form a clique by fault-prone directed communication links, f of which can be Byzantine faulty. We consider two synchrony models in this work. In the synchronous model, communication happens in rounds and all nodes proceed in lockstep. In the asynchronous model, nodes may proceed at an arbitrary speed and there is no known upper bound on the message delay. Let me introduce the GAB faulty link model. As I mentioned before, we have two key features: global constraint that allows up to F links in the whole system to become Byzantine faulty, and asymmetry indicates that when a link is corrupted, only one direction is corrupted. Moreover, link faults can be static or mobile. In the static model, the set of faulty links always remains constant during the execution of the algorithm. By contrast, in the mobile model, a fault can affect different sets of links at different times, and nodes do not know whether a link is faulty or not. Due to the limit of time, we will only introduce the GAB static model in this presentation. The motivation for this study was that in a complete communication graph, it is more natural to argue that the Byzantine adversary can corrupt any link in the whole system than to assume the local constraint on the number of faulty links attached to each node, since the cost to corrupt any link is likely to be similar. Besides, asymmetry is another important reason that our model has more practical applications. For example, in the wireless network. Also, we can see a Byzantine link fault as a man-in-the-middle attack, which steals node A's identity and sends messages on A's behalf. The asymmetry in the communication links makes an asymmetric fault realistic in this attack. So we discussed the works focusing on faulty link model or message adversary. Santoro and Waldmeyer proposed the transient Byzantine link failure model, where a different set of links can be faulty at different times. Their results are not tight. Hence, the conditions are different from the one identified in this paper. Essentially, our GAB sync mobile model is the same as their fault model. Zhang and Vadia studied the approximate consensus problem, whereas we consider exact consensus in this paper. Billy and his partners proposed a hybrid fault model that adopts local asymmetric and Byzantine assumptions. In contrast, we have the global constraint, which makes the algorithms and lower bound proofs sufficiently different. Charenbost and Schipper proposed a hybrid model called Herd-off model, which captures both the link and node failure simultaneously. The failures are assumed to be benign in the sense that no corrupted message will ever be received in the network. Fulger and his partners worked on approximate and asymptotic hit consensus in dynamic networks, where all nodes are fault-free, but the network or message delivery is controlled by a message adversary. Therefore, they are very different from our GAB model. And now we have this question. Why is it non-trivial to solve something in the GAB model? Recall that the GAB model allows F global faulty links, and now consider a synchronous system with n equal to 2F plus 1 nodes and F static faulty links. It is possible that, first, a node cannot send out anything reliably if F of its outgoing links are corrupted, or second, a node cannot receive anything reliably if F of its incoming links are corrupted. One key challenge for us is to devise algorithms that utilize one-way information flow to solve consensus. This becomes even more challenging when faulty links may move. We also investigate the problem in asynchronous systems. We'll talk about this later as a future work in this presentation.
Now we present our results. First, we prove the lower bounds of the three models, GAB synchronous static, GAB synchronous mobile, and GAB asynchronous static, and the lower bounds are 2F plus 1, 2F plus 3, and 2F plus 2, respectively. We also proposed an algorithm that tolerates Byzantine failure in each model. In the rest of the presentation, we will focus on the GAB synchronous static model. Let's look at the GAB synchronous static model. It can be proved that n greater than 2F is a necessary condition for any algorithm to reach consensus under this model. Otherwise, suppose n is equal to 2F, then it's possible that for some node I has F faulty incoming links and F minus 1 correct incoming links. This means that the majority of incoming links of node I is faulty, so node I cannot correctly learn from other nodes. We also proposed two Byzantine tolerant algorithms under this model. The first one is the round-robin algorithm, which is based on a reliable broadcast protocol. The second one is the three-phase algorithm. This algorithm is based on further observations of the reliable broadcast protocol, and as its name suggests, it requires only three phases. First, let's look at the reliable broadcast protocol. Here's a simple illustration of how it works. The reliable broadcast protocol is a two-hop communication protocol. In other words, there are two runs. Suppose we have 6 nodes, as the graph shows, and node A wants to reliable broadcast the message M, and node B wants to reliable receive that message. In round 1, node A broadcasts the message M to its neighbors. Since we assume the network is fully connected, all nodes J not equal to A can receive the message M prime from A and stores M prime in the memory set, say R of J. And in round 2, all node J not equal to A will forward the received message M prime to other nodes. Then all nodes will receive and store message M double prime in the second run. At the end of round 2, each node will reliably receive a message depending on the messages it receives and stores in the memory set R. By default, node A reliably receives its own message M. And for node J not equal to A, if J stores at least F plus 1 identical messages in R, and say M star, then node J reliably receives M star. Otherwise, it reliably receives an empty placeholder. Now, let's observe some key properties of this reliable broadcast protocol. First, we can observe that from node A to node B, there are n-1 link disjoint passes. By link disjoint, we mean that any pair of the passes do not share any common links. As a result, we can see that every individual faulty link can attack and corrupt at most one pass from A to B. This is because all passes are link disjoint. Also, each pass from A to B corresponds to one stored message in the memory set of B. So there are at most F faulty messages in that memory set. These properties imply the following results of the reliable broadcast protocol. First, consider an easy case when n is greater than or equal to 2F plus 2. then there are at least two f+1 linked strand passes from A to B, and at most efforts are Byzantine 14. Therefore, B can always receive at least f+1 correct messages M sent by A, and this means B reliably receives M. Now consider a more interesting case when N equals to 2f+1. In this case, it is possible that node B does not reliably receive message M broadcast by A. However, any node must either reliably receive M, the correct message, or the empty placeholder. The reason is that any such node B can only store at most F40 messages in its memory, so it can never reliably receive a faulty message. With these properties, we can propose our first and simple algorithm, the round-robin algorithm. The idea is easy. In each round I, node I reliable broadcasts its current state V of I. And for every other node, if it reliably receives a non-empty message M star, then it updates its local state to M star. And this process is repeated for all N nodes. We can easily verify the correctness of the round-robin algorithm. First, it satisfies validity because all nodes can never reliably receive a faulty message. It also satisfies the agreement property because there must exist some spanning node such that all nodes can reliably receive its message. For the three-phase algorithm, we want to assume that for now on, N equals to 2f+1, because otherwise, if N is greater than or equal to 2f+2, then all nodes must reliably receive the correct message, and we can apply the previous result to easily show its correctness. Let's make some further observations about reliable broadcast protocol. There are three possible scenarios when some node S reliably broadcasts a message M. The first scenario, S1, is all nodes can reliably receive the non-empty and the correct message M from S. The second scenario, S2, is every node except for one node reliably receives the correct message M. And the third scenario, S3, is only S itself can reliably receive M, and all other nodes reliably receives the empty placeholder. We prove that S3 occurs on node S if and only if S has exactly F outgoing links. We can make a symmetric observation on the receiving node. So suppose that every node I reliably broadcasts a message M sub I, and there is a receiving node R that reliably receives messages from all these nodes. Again, there are three possible scenarios. The first scenario, R1, is that node R reliably receives the correct message MI from all nodes. And the second scenario is that node R receives from all nodes except for one node. And the third scenario, R3, is that R can only reliably receive non-empty message from itself. Again, scenario R3 occurs on R if and only if R has exactly F40 incoming links. We can observe a really important result. Let's again use the example of node A reliable broadcasting message M and node B reliable receiving from it. And the result is node B reliable receives an empty message from A if and only if there are exactly F40 passes from A to B. We can easily check this lemma is true because of our definition of reliable receive and our assumption that N equals to 2f+1. We can also calculate the number of such faulty passes from A to B. This equals to the number of faulty outgoing links of A plus the number of faulty incoming links of node B minus the number of overlapping faulty links, which are counted twice in the previous part. For example, suppose the red arrows represent the faulty links. Then node A has two faulty outgoing links, and node B has two faulty incoming links. There is one faulty link, which is link AB, and it is counted twice, so the total number of faulty passes from A to B is 3. Let's look at several preliminary lemmas that are essential for the algorithm. First, for each node I, one and only one scenario of S1, S2, and S3 occurs on node I. Similarly, this is true for the receiving node. In other words, exactly one of R1, R2, and R3 occurs on every node I. The second lemma is, if scenario S3 occurs on some node I, then for every node J not equal to I, scenario S1 must occur on J. This is true because we can recall that S3 occurs if and only if S has F faulty outgoing links. So for any pair of nodes JK such that J is not equal to I, there can never be F faulty passes from J to K. Similarly, if R3 occurs on some node, say J, then for every node I not equal to J, R1 must occur on I. Third, S3 and R3 cannot occur simultaneously. More specifically, if S3 occurs on some node I, then R3 can not occur on any node, and the converse is true. Again, this is true because S3 occurs if and only if S has F faulty outgoing links, and R3 occurs if and only if R has F faulty incoming links. So the condition of S3 and R3 contradicts if we assume F is greater than 1. Finally, if scenario S2 occurs on some node I and R2 occurs on node J, then we have the following two properties. One is that for any node K other than I, S1 must occur on node K. And two is that for any node K other than J, R1 must occur on node K. These lemmas, especially lemma 2 and lemma 4, are essential to construct our three-phase algorithm. Now let's look at the simulated execution of the three-phase algorithm. As its name suggests, there are three phases. In phase 1, node 1 reliable broadcast is local message, local state, and in phase 2, node 2 reliable broadcast is state. The third phase is preserved for a specific node R, such that scenario R3 occurs on node R. Let's consider other possibilities. First, assume S1 occurs on node 1 in phase 1. Then, at the end of phase 1, all nodes will reliably receive the local state of node 1, and the algorithm reaches agreement. And in phase 2 and 3, regardless of the scenarios, the algorithm remains the agreement property because no node can reliably receive a faulty message. So we are done in this case. In the second case, let's assume S3 occurs on node 1. Then, by lemma 2, S3 occurs on node 1, which implies S1 must occur on every other node. In particular, in phase 2, S1 occurs on node 2. So again, every other node will reliably receive the local state of node 2, and agreement is achieved. In the final case, assume S2 occurs on node 1. In other words, there exists some node reliably receives an empty message from node 1, and let's call that node R. There are two possibilities of node R. The first one is that the scenario R2 occurs on node R. Then, by lemma 4, S1 occurs on all nodes other than node 1, especially including node 2. Therefore, in phase 2, node 2 reliable broadcast its local state, and every other node can reliably receive the local state of node 2. And the algorithm again reaches agreement. The second possibility is that scenario R3 occurs on node R. In this case, R will never reliably receive any non-empty message from any nodes except for itself. However, by lemma 2, scenario R1 must occur on every node other than R. This is equivalent to, say, as 1 occurs on node R. So if node R happens to be node 2, then node R will reliably broadcast its local state in phase 2, and we're done. However, if R is not 2, then we want node R to be the node that reliably broadcasts its local state in phase 3. Since as 1 occurs on R, the algorithm will reach agreement at the end of phase 3. Unfortunately, there can be at most one such node R, and node R is uniquely defined if it exists. Such analysis suggests that if our algorithm can identify such node R and let a reliable broadcast in phase 3, then the algorithm can satisfy the agreement property. Let's look at the formal definition of our 3-phase algorithm. In phase 1 and 2, node 1 and 2 reliable broadcasts their states, and every other node updates their state if the received message is non-empty, and otherwise it increases the counter n of I by 1. We need to notice that ni is actually an indicator of the receiving scenario of node I. At the end of phase 2, n sub I equals to 2 if and only if R3 occurs on I. This suggests that in phase 3, if there exists a node R such that n sub R equals to 2, then scenario R3 must occur on that node R. And if node R reliable broadcasts its local state, according to the previous result, every node reliable receives that state, and the algorithm can reach consensus.
We still have some exciting future work for this problem. The first one is how to adapt the mobile model to asynchronous systems. For example, we may consider the relative speed of moving compatibility of faulty links and message delivery. The second one is the lower bound of synchronous mobile failure for general algorithms. Please refer to our full paper for more details. Thank you for listening.